Share the screen. All right, so we're sharing now. I don't know why this TV isn't working, but that one. So today we are going to cover your third algorithm, which is called Hopfield networks. This one. This is where the first set of lectures on neural networks starts to pay off because this algorithm is similar to the perceptron. So, we are now covering neural networks as a sequence, and so everything just is going to be familiar, right? So going forward, we're still going to be talking about neural networks, but now you have maybe the perceptron was very new and everything was strange about it, right? But now with Hopfield networks, there's going to be things that are similar to the perceptron, and then there's going to be new things, right? So it starts to build, one algorithm on top of the other one. And so that's the nice thing about this sequence. Does that make sense? So that's what we're doing now. So we're covering Hopfield networks. So I provided a link here, and it takes you to the repo, the Machine Learning Foundations repo. You can see that here. Here, this link here is the code that we're going to cover today of the algorithm. We're just going to go through it. And then I'll start talking a little bit about the Hopfield network and how it works. Okay, so very interesting thing. Hopfield networks are actually a technique that when it was proposed, so the perceptron was proposed in the 40s, it was implemented in 1957, right? Hopfield networks were proposed in the 80s, I think 81, 82, and this technique actually won the Nobel Prize in physics. Okay, so this is if you've ever wanted to understand something that won the Nobel Prize, here you are, right? So we're going to look at this idea. So this is very interesting. This is before, so it's somewhere between the perceptron and stochastic gradient descent, which was proposed by Geoffrey Hinton, which also won the Nobel Prize. But this is a little bit before that. And so these are essential groundbreaking work, and it's just basically a neural network with some capability. So obviously Hopfield network by John Hopfield, who's a professor, I think, at Princeton, somewhere like that. All right, so we'll cover this script, and actually I made this example in terms of anomaly detection, so it's also related to cybersecurity, so that will be the example that we're going to cover, although when Hopfield created this type of a network, he was trying to explore or try to get better understanding of how the human brain works. So this algorithm is actually related to memory. All right, so other examples that we've done try to predict things. This one, on the other hand, is about a representation of how our memory works, if that makes sense. Okay, so it's it's called an associative network, and essentially it's trying to mimic the way that our memories are created, right? So we have a neuron that's connected to our eyes, and then we have another neuron that's connected to our nose. So whenever we see, for instance, with our eyes, a banana, yellow, right, that neuron might fire, right? The one that recognizes the color yellow is associated with banana. But as it turns out, a neuron that's next to it and that's connected to our nose, right, might also remember the smell of a banana, right? And so this is what happens to us a lot of the time when we listen to a song and somehow remember a fragrance, right? Or remember a smell or something from your childhood, right? You see something and it's like you have this, wow, I feel like I'm there or whatever. And it's this idea. Obviously the human brain is much more complex than a Hopfield network, but it is a very groundbreaking work that tries to study this idea. And so that's what we're going to look at. And so we're going to look at it in the context of anomaly detection, which makes a lot of sense because an anomaly detection is like memory, right? So we know what something looks like, and then we're just going to study, okay, does this new item look similar to that? Or is it an anomaly, right? So it's a little bit of this idea of memory. So I provided all my notes for this one on the GitHub. So I've written down, provided some diagrams and some of the operations, and it's very straightforward. And then we're going to look at our Jupyter notebook essentially. And so that you have a concrete example, as I said, it'll be related to anomaly detection, which could be applied to network security or malware detection or something like that. But but I also actually do have an example of images. So if time permits today, we're going to get to that as well, because as you know already, you can take an image that is two-dimensional and just spaghettify it into a vector. So that will be consistent with what we are doing. All right, so let's get started. So this is the second in your sequence of neural networks. We started with the perceptron, first one. This is Hopfield networks, the second algorithm. From here, we would have, historically speaking, something called Boltzmann machines, then restricted Boltzmann machines, then stochastic gradient descent by Geoffrey Hinton. And then after that, we're just in PyTorch. So you're using state-of-the-art algorithms, and our sequence goes to multi-layer perceptron, to deep learning, and so on. Yeah, so that's kind of how it is. So as you can see, the main focus of the second third of the semester will be on neural networks, okay? All the way leading up to deep learning. After that, the last third will cover something called transfer learning, and we will explore one transfer learning algorithm called the ResNet and something called CNNs, which is part of it as the advanced topic. As far as traditional machine learning algorithms, within the neural network sequence, we'll cover linear regression and logistic regression. So those are like traditional algorithms, and you'll see that they are essentially neural networks as well. And then the one outside of neural networks, a few of the techniques that I still want to cover are XGBoost and Bayesian techniques such as naive Bayes. All right, so that's essentially what we've got coming up. But for the second third of the semester, the focus is to continue with neural nets. And I want to get into PyTorch as soon as possible. Okay, any questions so far? All right, so let's take a look at the notes. So Hopfield networks. As I said, proposed by John Hopfield. He's still alive today. There's a nice interview if you're curious on Lex Friedman, the Lex Friedman podcast. You can check it out. Just Google John Hopfield, and he gives they basically talk about this technique. So it's kind of neat that he's still alive. As I said, he won the Nobel Prize in 2024 for this in physics. All right, so Hopfield network. So as I said, we've discussed the perceptron already, and now it is time to connect multiple neurons together. All right, so if you picked up on the perceptron, it was just one neuron, okay? We were trying to do a lot of things with just one neuron. Now we start connecting multiple neurons, multiple layers. That's essentially the idea. And all that knowledge, I would say that at least 50% of the knowledge that you acquired from the perceptron carries forward going forward. All right, so now it's time to connect multiple neurons together. We now make the output of one neuron into the input to another neuron. So that's essentially how we connect things, right? So we have a function, give it an input, get an output, and that output becomes the input to the next one, and so on. Okay? So we now make the output of one neuron into the input to another neuron. As this allows us to create neural networks, and as I've said many times, if you think of ChatGPT or something like that, it's the same as this. It's just incredibly deep. And instead of having 17 weights as we do with our perceptron homework, we have 671 billion, right, of those. So it's a lot of weights. All right. So this allows us to create neural networks. So neural networks can be of two types, okay? So this is an important one. So there's going to be something called feed-forward nets, and you'll see this word a lot. We'll even code it, and we'll create these functions, and I'll say an MLP is a feed-forward neural network. And so this is a term. So the idea with a feed-forward neural network is that it's all in one direction, all right? So which the perceptron was. So you had your inputs, and they move in that direction. And then when we're updating things, we do something called backpropagation. But Let's just concentrate on the inference part right now. Get input, it moves forward. So those are called feed-forward nets, all in one direction. Maybe in your data structures classes, you learn of something called a directed acyclic graph. So that's essentially the type of network that this is. Just a normal network. The other option of a neural network, the other type, is what is called the feedback net. Okay, feedback net. So obviously feed forward, just all the connections go in one direction. Feedback, you have both directions, or one thing can go back or something like that. So essentially the definition of this one, if it's not a feed forward network, then the network is a feedback network. Couldn't be simpler, right? So it's either something is strictly a feed forward net, otherwise it is a feedback network. Most of the networks that we will study this semester, most of the neural nets will be feed forward, which, with the exception of today's network, which is a feedback network, essentially. So this classification depends on their connectivity. So I drew a diagram here so you can see. So A is a feed forward. So what's important is look at the arrows. So I have two neurons in the input. So I have two neurons in the input here. Then I have another layer and then the output layer. You see that? So notice the direction, it just goes in one direction like that. All links are in one direction. Does this make sense? So it goes, the inputs that come in here just have one direction to go, which is this way. And then these inputs just have one direction to go, which is this way. Okay, so this is a feed forward network. Most neural networks will be like this. All right, then we have the feedback network, B. And you can see this one, it only has three neurons, but essentially there's obviously the feed forward direction, but then we have a feedback direction, as you can see. And this is important because this idea is trying to represent memory, right? As opposed to trying to, almost like with electric circuits, trying to move the current forward in some direction. This one is trying to, connect everything together and be a representation of memory. But that's the difference. So they have been used so Hopfield networks have been used to study what's called associative memory. Okay, so we'll look at this idea a little bit. Memory can be, and as I said before, memory, you can make the analogy and compare it to anomaly detection. So a lot of the time, it's nice to study Hopfield networks for memory and how that may work in the human brain. But essentially, if you apply it as a tool, you end up using it like for anomaly detection and things like that, as I will show later. All right, so yeah. So the Hebbian train, that's an idea from a gentleman named Hebb, but he just talked about associative memory, essentially. And this is the example, the classic example that you hear about is this idea of a banana. So in this example, we have, why this is a feedback network. You can see we have one, these circles are supposed to be neurons. This neuron, something in the brain somewhere or in the network, but it's connected to an input related to the nose. And so it's related to the smell of a banana. Whereas this one over here, this neuron is connected to some sensor, which is, like in a human body, this represents like an eye, and you see the color yellow for a banana. So they're feedback because the nose might smell a banana, and so it feeds, once this activates, the activation can propagate to the other neurons. So it can go in that direction, but if you see the banana, then this activates, and the activation may propagate to the other neuron. You see that, guys? So it just means that one affects the other, right, in the structure of the neural network. Whereas in the feed forward, once you're over here, you can't really activate the neurons before you. There is no connection back. Got it? So that's essentially the idea. So the activation propagates. All right, so today we're going to look at a new operation of, that we're going to need of a tensor operation, but it's pretty straightforward. I have it written down here. And actually, this operation is done in Numpy. It's called the outer product, right? So this is the way that we can create the connections, basically. So the way that you can think about it is all of these are neurons, right? So think of all of these as little circles, and then we need to have a connection between each one, which is the link, right? And that link is the weight, essentially. So weights, once again, right? We just want to establish how strong a connection is between, these two neurons. So for instance, here, the connection between these two is probably really strong, right? But what if this was like banana and this is, I don't know, quantum physics? There's no real connection between banana and quantum physics that I know of, so it would be smaller weights. Do you see? Or some weird thing like that. But so that's essentially the idea, that this is still, neural networks are just about that, like the weights between one neuron and the other, and we're just going to quantify that in some little table as we have done before. Any questions? And we do these matrix multiplications. This just happens to be a very easy way to create this, and it doesn't matter what the size of our vectors is, we'll just be able to create this table that links one neuron to the other so that we can then, using the algorithm, basically decide how to use the information. So here's a little bit more. So Hopfield networks are sometimes called associative memory networks. As I said, John Hopfield won the 2024 Nobel Prize in Physics for this work. So this last year, both John Hopfield and Geoffrey Hinton were both nominated for the Nobel Prize and got it. They can be related to information theory because they can be used to store and retrieve information. So it's the same idea as, when you study, RAM memory, right? RAM memory or the hard drive or whatever it is. Those are also storage devices. As you guys know, they just happen to be a different construction, whereas this one is trying to achieve the same goal, but just using neural networks instead of the normal binary circuit things that we're familiar with on RAM and the hard drive. Okay, so that's the idea. The number of neurons can determine the amount of information that can be stored in the model, right? So the more neurons you have, the more memories you can store. And in fact, you can quantify that, right? So you can use a metric to estimate how much information can be stored in one of these networks. Now, to do the essential operation for this to work, everything in the Hopfield network, I would say, is very straightforward. It's very easy. And there's like two ideas that you have to understand. And the ideas are that you have all these neurons, right? It's not a direct feed-forward network, but it's got feedbacks. And so you're just trying to establish the strength or the weight between one neuron and the other. If you have that information, then you're able to use the algorithm. So one simple idea is, if we have V1, V2, V3, and then we have V1, these are U1, U2, U3, and this one is V1, V2, V3, V4. So just think of them as neurons. 3 neurons followed by 4 neurons or whatever it is, right? Or however they're organized. And we just want to compare all of them, like almost calculating a distance metric between them, right? And so we need to create some kind of a convenient table that can store that mapping. And so as you can see here, we take, with this approach of the outer product, we can do that easily for any vectors, right? So you can see how it does U1 to V1. So you can see it compares U1 to V1, then U1 to V2, U1 to V3, U1 to V4, then U2 to V1, U2 to V2, U2 to V3, U2 to V4, and finally U3 to V1, U3 to V2, U3 to V3, and finally U3 to V4. So it just compares all of them, and the weights on the diagonal, the weights on the diagonal are always going to be 0. So you don't want that in the algorithm. Let me go back. All right. So we'll see how that can be done in the algorithm as well, and it should be pretty straightforward. So essentially what we're doing is we're establishing a table, if you want to think of it that way, of comparing neurons, all the neurons to other neurons, and just figuring out what the weights would be given some learning rule. Just like the perceptron had its learning rule, here we're going to have a learning rule that somebody very smart, John Hopfield, invented or discovered, however you want to put it. So to create this table, I mean, obviously you could create this manually with many for loops and so on. It would be highly inefficient, or you can just use the outer product operation. So Hopfield networks use the outer product multiplication to calculate the weights matrix. So I will demo that, and I believe the function is called NP outer or something like that from Numpy. So we'll just use that operation, and we'll create that. So the outer product is an operation in linear algebra, which given two vectors can return a matrix. The outer product operation can be seen in the next example. So this is the one. The algorithm for doing this is like this. So the weights are calculated via an outer product of the input vector and the transpose of the same vector. The identity matrix is subtracted from the resulting matrix and can be seen in the following formulation. And we'll see why this is essentially to have zeros. We want to have zeros on the diagonal, basically, so that there is no weight. The algorithm does not want weights for these values here in a diagonal, a square matrix. All right, so this is just to illustrate the basic logic. All right, so here are some important points to note about Hopfield networks and the code. NP outer produces one product between each possible element pairing from two tensors, right? So it's, that just means every neuron is compared to every other neuron, and we want to find what those weights would be through the learning process. And that can change, right? So the values of those weights, it's not like it's set in stone. If it's an iterative process. So if you do 20 iterations, you have a set of weights. If you do 100 iterations, then the weights change a little bit. The idea is that, the more training you do, the more it converges to the correct answer, right? Which in this case, it's really just, it captures some representation in memory, all right? That's essentially what it is, okay? And that's why this is applied to anomaly detection, because if you think about it in terms of like images, right? You give it pictures of images, keep giving it pictures of images, and they're all images of cats. So when you give it another cat, because it's a type of a memory, it's going to say, oh yeah, I think this kind of looks like a cat. But now you give it a picture of a boat, right? And that boat goes into the memory, and it's going to compare it, and it's going to say, actually, this looks a little bit different from what I understand to be a cat. So that's essentially how it works. Got it? So something activates if it looks like what you have in the memory. And if it's too different, it'll still activate, but the weight might be lower or something like that. So we'll need to have a metric for that, which is, we'll see how that works. All right, so NP outer produces one product between each possible element pairing from two tensors. NP outer is used for the outer product. So this is actually the Numpy command that we will use, right? So the code. And so the intuition is like a pairwise distance metric. So just think of it that way, is just how strong is the connection between this neuron and this neuron. So this can help us to find the distance between each pair of point values. So we'll see that. So that's essentially the notes, right, on the Hopfield network. And now the next thing we're going to do is we're actually going to code this up and train it with some data and just get a feel for how it works. And remember, since the idea is kind of to store memory, we're going to use it as an intrusion detection system. All it can tell us about a sample is how close it is to what you have in your memory. You see how nice that is? It's like you're saying, I have this memory of what classical music sounds like. I mean, you could encode something like that, right? And then you hear, I don't know, what's another country music, and then you're going to say, well, actually, this does not sound like that, right? But we have this mechanism, this algorithm that helps you to do that for anything. It could be music, it could be poems, it could be networking data, whatever it is. All right. So let's take a look at it. That's why was so amazing, especially back then in the 80s when it was invented. All right. So the next thing we're gonna do, so we're gonna use this script. I provided the link up here. So make a note of that. You can click on it. Okay. And it's gonna take us to my code. So I'm gonna start Anaconda and we're just gonna go through it. I created the data randomly, so that way we don't have to read any files or anything like that. We're just going to go through it, and you'll see that it's really not difficult to understand how it works. It's pretty straightforward, and the nice thing about these things is they start to use the same template for everything. So everything is going to start to become very consistent. All right, at least for the second third of the semester. All right, so here it is, Hopfield Network. So I'm going to go ahead and start Anaconda. Okay. So I'm going to click on this Anaconda 3, Anaconda prompt. My computer has been very slow. All right, so we're here, DIR. I'm going to CD into the desktop. Also, before I forget, for next week, next Wednesday, do you remember we had talked about some of you demoing your assignments, both your Weka and your PyScript one? So I think you had asked for bonus points. So I can do that. For those of you that present next Wednesday, I can give you like a few bonus points. If you have it available, yeah. Yeah, if you have it available. I know some of you have finished already. Yeah.
So are you asking for like a presentation?
Yeah, just a very informal presentation. Just show us what you did.
Oh, so no like slides or show?
Well, your PDF is fine. Yeah, you can just use your PDF and it's really just about like discussing what you did and with Weka, how it was. I think I've graded all that, but still, it'd be nice to share the information. And then for the PyScript also, just to see how people are approaching it today. Because I'm gonna do something with images today. So I'm also going to, that code you can actually use for your PyScript assignment. So I just want to show you a little trick that you can use to maybe make those L's or T's into an actual image. And that might look a little bit better. Okay. It's up to you guys if you want to use it or not. But I will remind me when I'm doing the image towards the end of class today to make that conversion, which is just 3 lines of code. All right. So yeah. So please, if we're going to plan that some of you will demo next Wednesday, either your Weka or PyScript, just so we can have a nice discussion about it. Got it? All right. Great. So let's go ahead and continue here. So I'm going to CD into my ITS 365 2025. Yeah. All right. So in class perceptron, iris, tensor ops, KNN. So this is your third algorithm. I'm going to call it Hopfield networks. So let's instantiate the environments, conda environment list. Pi 37. Yeah, 2025. So conda activate Pi 37 2025 ITS 365. TLS, TAR. All right, here we are. So I'm just going to start the Jupyter Notebook. And we're going to start writing the code for this. So Hopfield, as you can see, the Jupyter Notebook is provided. I'll just do the exact same Jupyter Notebook back here. So I'm going to create. This is going to be done from scratch in pure NumPy. So it's going to be Hopfield networks. And the applications, I said, even though it's associative memory, the memories that we have are going to be of network data, essentially. It's like we have a brain that understands what certain network data looks like. And then we're going to use it as an anomaly detection system. So it's scanning the network, and every new trace of network data that comes in, for instance, is going to be grabbed and compared in this memory. And this memory is going to tell us if it thinks that this is, how close. It's going to give us a metric, a value that says how different or similar this new thing is to the memory that we have of the network. Essentially, that's it. Okay. So that's called an anomaly detection system. So I'm going to grab, I don't need, I'm using torch in this one, I suppose, for a conversion that I did, but it's essentially a light. All right, so I'm going to go ahead. Remember if I've installed PyTorch. Find out. So import torch, import NumPy, run it. So this is solid currently. I'm going to rename this in class Hopfield next for anomaly. Anomaly detection, rename it right here. Anomaly detection with Hopfield networks. There we are. So then I'm going to just cell type. Here we are, and we have the libraries already installed, NumPy and Torch. Okay, so now we can get started. This is the whole network. As you can see, that's it. Pretty straightforward to use a Hopfield network. The algorithm. This obviously, as I said before, it makes a lot of sense in neural when you're dealing with machine learning to use object-oriented programming. So here I'm just creating a class called HopfieldNet. You can see it's got a constructor, it's got a train function, and then it's got like the reconstruct function, which is like the testing function. So essentially, this is where we give it a pattern. So let's call everything a pattern. We take a new pattern and query our memory. Sometimes this is called retrieval, right? So that's another term that's used, like information retrieval. So you're just taking a new pattern, almost like Google, right? You do a search in your Google and then you send it to the memory and you try to retrieve that information. So let's go ahead and copy this one, and then we can discuss it essentially and see how it works. So I've created this class, HopfieldNet. It's got the constructor. So this is the size of the pattern. And what that means is how many elements we're going to have. So in this example, I'm just going to have 6 to keep it simple, right? Very small. But if it was an image that is 24 by 24 or 28 by 28, right? We can, from a matrix representation, we can make it into a spaghettify it into a vector representation, and then it would be 784. You see what I'm saying? So anything that we take into this we're going to do that. So this size variable here is essentially that, the size of the pattern input that's coming in. Okay. So let's take a look at the constructor, make it a little bit bigger maybe. So initially we just initialized the parameters. So if you're not familiar with these init functions, you'll get used to them. We're always going to do this going forward in our neural networks. We're going to have two functions. One is going to be the init function, and then the next is usually going to be like forward or something like that. But we can have as many functions as we want in here, right? So here in this one, this is built in such a way that it has the constructor, the training function, and the reconstruct function. So let's take a look. So init, whenever you do a class in Python, you'll always initialize like this constructor. These are two underscores, and then these are two underscores, and then you have the word init. So it's kind of a built-in representation. Obviously, we have self here. And then this just, when we initialize it, we want to specify the size. This essentially tells us the size of our matrix that holds the weight of our memory. Okay. So we're just going to take size and save it and just self.size. And then we're going to create this matrix self.weight, which is np dot zeros, which is going to be size by size. Okay. This is what allows us to compare the patterns. Does that make sense, guys? To create that matrix with the np outer product. All right. Great. Excellent. All right. Once I have that, and that's essentially it. In this example, that is simple actually. That's essentially what's happening is we have this weight matrix, and then we can query, we're using it to store our memories, and then whenever we have a new pattern, we just query it. So then the train function is going to be this one, and essentially here we provide the training data. So this is going to be, think of it as a list of patterns. If it was images, we'd have like 100 images, right? So these are the patterns that are coming in. You can see that essentially what we do with this approach is we take, we iterate through that list, right? So we're iterating through all the patterns that we have. So maybe it's a list of network traces or network representations of network data. We're iterating through them, and notice how straightforward this is. So we take the pattern that comes in, and we calculate the NP outer product. That's the operation that I showed you at the beginning, right? So we do that NP outer product matrix multiplication, and it creates for that vector a matrix that is size P by P, right? And then we also have a matrix self-weight, which is of the same size because we initialized it here to be. So this size and size of this is the same. So we have the weights originally are 0. When we get a new pattern, we add it to that set of weights, and then we get another pattern and we add it to that set of weights. And we just keep doing that as we're training. And that's like essentially it. Okay, in its simplest form, this is how you train the Hopfield network. Does that make sense? All right, and this is trying to capture memory, and surprisingly, this works. Right? Surprisingly, this works. All right, so all we're doing is initially remember these weights are 0. We get the first pattern, we calculate the outer product, right? And we get the little matrix, and we'll demo this in a little bit. And then we just add it, and then we have the next one, and the weights are starting to store the information. Once that's done, we don't want self-connections, right? So we don't want connections between the same neuron, right? Because this is, it's the vector is comparing to itself. So we want like a value where those two meet. And so we use this approach, which is that idea of the minus identity matrix that you saw in the equation. So that's something I had, I think, here. So that minus I. It's a minus I that you see there. So I'm doing V outer product of V, right? The same vector, minus which these two vectors, when we do this operation, create a matrix and a square matrix, and then we just minus the identity matrix, which essentially just has ones on the diagonal and nothing else. And so we serial those out, essentially. All right, so that's the idea. So we do that with this code here. We have our in class. So after we've gone through, so notice we have a for loop for all the patterns, right? And we're adding them to the weights matrix. Once that's done, we take the weights matrix and we fill the diagonal with zeros so that we don't have self-connections. Okay, that's it. That's essentially it. And then after that, we have a type of a normalization where you can see we have the weights and we divide them by the number of patterns. Okay, because we are adding, right? So we are, we add 10 or 15. So then we just want to divide by the number of patterns that we have, and this will apply to all the weights. And that is, in its simplest form, as I said, the Hopfield network training function. This is way simpler and less sophisticated than deep learning or multi-layer perceptron, which is the next thing we're going to look at. But it still is a network. It still has weights. The perceptron algorithm is even more complex than this. This is simpler, but this was a different thing, right? So this was demonstrating memory, this idea of associative memory. It was also not a feed-forward network, but this is a feedback network. So it's a little bit different. So essentially, this is how we encode all of our images, let's say, into our memory or whatever it is. So now you can imagine how somebody is saying, we have a huge brain, right? And some areas hold this little bit of information, other areas hold other information, and essentially we can have trillions of memories, right? Which we probably do as humans. And so now the key question is, how do we know where to go when we want to retrieve something, right? So that's the mystery, probably. Like our eyes go to a specific part of our brain, and then, our ears go to somewhere else in our brain, but they would go into this associative network and try to retrieve information, try to activate some kind of a function. Okay. So that's, this was groundbreaking work in the early 80s. All right. So that's how we train it. So that would train the Hopfield network. And then the second thing that we would do is now we want to, retrieve a pattern from memory. So in that case, it basically, the algorithm says that we're going to do this several times. So we take a number of steps. We give it a pattern. So something comes in, let's say a new image comes in or a new piece of network information. And we're going to multiply. So you should be familiar with this function already, the NP dot, because we have discussed it before in the context of the perceptron, right? So that's what I was saying. We build on top of the things that we've talked about before. And if you notice, it's a matrix multiplication. Almost everything. And as you will see in machine learning, deep learning is always some kind of a matrix multiplication that efficiently gives us the information that we want. So here we take the weights and perform this dot product between the pattern and the weights, right? And once we have that information, that starts producing a value, okay? And what, as we will see later on, it's kind of like the way that it works is, we have a pattern that comes in, and that pattern goes, you do this operation multiple times, right? And essentially, eventually, that pattern should become very similar to the patterns that you had in memory. So you're going to compare the difference between the way the pattern came in and the way it comes out after performing this operation. Do you see what I'm saying? So the closer they are, the more that is like the data in memory. So we'll see that in a second. But so I'll come back to this one because it might be a little bit harder to understand. But this is the reconstruction process for the Hopfield network. So hopefully the part that makes a lot of sense is that we take the patterns and encode them into this weights matrix, and then we're going to repeatedly transform the pattern by performing this operation. And then we look at how it was initially and how it looks after, and we're going to take a measurement of that. Okay. And so that is the algorithm. So we'll see that. So anyway, these are the three parts. Let's go ahead and run it. So that ran fine, no errors. So now let's go ahead, go back to the code. See that in a second. A lot of anomaly detection systems, by the way, are similar to this. All right, so we have the Hopfield network. Now, if you notice, I'm going to create just some random data. Go over here. You can see the data also in the Hopfield network in its classic form, it's binary like this, ones and minus ones, okay? So we have data, it's just a Numpy array, right? These are the samples. So I have sample 1, sample 2, sample 3, and sample 4. And remember, this is a memory that you have of a specific thing. Does that make sense? Like maybe imagine that you're creating one part of your brain that has this associative memory of what a cat looks like. And then you have another part of your brain that has this associative area of what a banana smells like. It could be whatever it is, but give it a lot of examples of that until it starts to capture that memory, right? So in this particular example, it's, as I said, a network, some kind of a thing. So use your imagination. Every pattern here has 6 features. And these could be like maybe a question such as, was this TCP? 1. Was this a lot of bytes? 1. Was this encrypted? 1. Was this, did it come from a friend? -1. Do you see what I'm saying? So you're encoding the features in some way, such as this, right? But one thing that I did on purpose when I created this data set is that they are similar. They do have a similar look. So all of these are ones, all of these are ones. Here I have a -1. Then I flip the bit here, and this -1 is now a +1. And these are all ones. So oh, sorry, no, this one. So this is a -1. Here I made this one +1 and the other one's -1. Do you see that? So I'm trying to create this specific pattern that, so that when I give it, so they all have a certain feel to it, right? And then I will provide a sample that looks like these, and I will also provide a sample that does not look like this, right? So that one would be what? More anomalous. You guys understand? And so obviously I'm going to test that the more anomalous one should look more different than the similar ones. And that's essentially what we're doing. And testing this out as our associative memory. So I call these normal, all right? So these are normal traffics. So I'm going to hit run. 6 is just a choice. As I said, this could be any size. We can have 1,000. It's perfectly fine. Okay. So I hit run. So now let's go ahead and take a look at the data, as I often recommend we do that. So I'm going to do this one over here. So that's, we're just going to print the shape and also print the data itself. So it's 4x6, no mystery there. 4 samples, each of size 6. Remember, that has to be consistent as always. And then the data, we're just seeing it as is. Okay. So now, this is our data. And if you look now, I'm going to proceed to kind of interact with the Hopfield network we're going to instantiate. So I created my class for the Hopfield network. It's over here. Now I'm just going to instantiate the network. So there it is. I call it Hopfield. I invoke the class HopfieldNet, and I specify that the size is 6. Why is the size 6? Why did I set this value to 6? Yes, please.
That's the Y of our shape.
X and Y, right? Exactly. Because every pattern has 1, 2, 3, 4, 5, 6 features. Exactly right. If these were images, 28 by 28, when we spaghettify them, they would be 784, right? then in that case, if I was building an associative memory for that one, what would be the value of this? 784, right? 28 by 28. Got it, guys? Yeah? All right, great. So we always have to be consistent. That's the one thing that we can't change, but we can have multiple associative memories. Think in a network environment, it's like saying, okay, I have anomalies for SSH, I have anomalies for DNS, I have anomalies for HTTP. So you just create a whole thousands and thousands of memories of what something looks like. And then when you get a sample, you just run it through all of them, right? And you get the feedback that you want so that you can what do you call it? Highlight or find something anomalous, essentially. All right, so I instantiate my Hopfield network, and then I'm going to print the weights of the Hopfield network. So I'm going to go ahead and do that. And you can see the weights are, this matrix is 6 by 6, right? So you guys see that this is the result of that outer product operation so that we can compare all the neurons, right? That's what I'm doing here. Notice there's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And essentially now, for this particular problem, the weights are currently 0, but I'm going to start training it, and I'm going to start to create the memory, okay? So I'm going to go ahead now, and I'm going to go back to the code. So we visualized it, and now notice it's very straightforward. We're going to run the training routine. So hopfield.train, we train it obviously with this data that I created here. And essentially, I wanted to create a memory of what that looks like, okay? So that I can later retrieve and query things with it. I'm going to go ahead and do that. And, no errors. It finished. It's a pretty small data set, so it's done. Any questions so far? There you go. So you just trained a Hopfield network to encode some memory. Now the key that you have is now you just deploy it, right? You deploy it in wherever you want, and now it's going to get new inputs. Sensors are going to capture new things, and those things are going to be compared with the associative memory, the Hopfield network. So for instance, now we can proceed to test the samples. I'm going to need a function called the Hamming distance. It sounds way more complicated than it is. So it's a very straightforward function. All right, so the Hamming distance essentially it takes in two vectors of the same size. And we're going to see this. So remember that you're going to get an input vector, a new pattern that goes into the Hopfield network, and the Hopfield network will perform multiple matrix multiplications. And it produces a vector of the same size. So then what you do is you compare the two, right? It's like it's reconstructing it, if you will, to look as much as possible like the data it knows, right? If the thing looks like what it knows, it's going to be very similar. The input and the output are very similar. But if what you get is very different from what it knows, it won't be able to make it like what it knows. So then it's going to look more different. All right, so we're going to see that. But we use this nice function Hamming distance to compare the input and the output of the Hopfield network when we're doing the retrieval process. And this is a very well-known function called the Hamming distance. It essentially calculate the Hamming distance between two strings. So this is actually to compare how similar two strings are. So for instance, if I give it the word hippopotamus, right? And I give it hippopotamus in plural or something, it's just going to look at how different they are versus hippopotamus and helicopter. Oh, actually, those two are similar, right? And then hippopotamus and what's a word that's really different to hippopotamus? Giraffe, right? So if I give it hippopotamus and helicopter, it says that the difference is maybe 2. But if I give it hippopotamus and giraffe, it says the difference is 4. So what does that tell you? That giraffe is more different than helicopter from the original word hippopotamus. Does that make sense, guys? Yeah. So that's essentially what this is doing. It's actually for strings, right? Yeah. So the Hamming distance between two strings. So essentially here is the definition of it. We don't have to code it from scratch because Numpy does it for us. Count non-zero wherever it takes A and B, and it just says where they're different or equal. You see that? So it performs this operation, and it just says, tell me if these are equal or different, and then essentially it counts the non-zero values, so the ones. So it's a type of an XOR to find differing bits, and then you count the number of ones. Okay, so we can do this also this function, but essentially that's what it's doing. Any questions? Remember, as I said, we're reconstructing the input, right? And the goal is that it should look like what's in memory. All right, so we have the Hamming distance over here. So I'm going to run the code for this one and load it into memory. Now that I have that, let's go ahead and run two patterns. We're going to run one pattern that should be similar to our memory. So I'm going to try to do that here. I'm calling it the normal test sample. Okay, so I'm going to call it the normal test sample. Oops. So this would be normal, not anomaly. Norm sample, root word. So I'm going to do markdown here. Run. Okay, so we're going to go ahead and so this is a test sample. So my test sample, I just handpicked it, is 1, 1, 1, minus 1, 1, 1. So if you look at this sample, I intentionally made it to look like this data, right? So if you notice, one thing I've done is that the first two columns and the last two columns are always positive, right? So that's kind of like the pattern that I added in there. And you can see this one has the first two are ones, the last two are ones, and then this can flip either way. So it's a similar pattern, and that's why I'm calling it a normal, not a. Okay, so that's one part of it. And then if you notice, all I'm doing is I'm calling the Hopfield network, okay? And I'm going to reconstruct. Essentially, I give it this pattern, and it's going to compare it to the weights by performing a matrix multiplication. It does that in a loop, so you can control that, by the way. So that's one of the things we had in here is the number of steps is set to 10 current. Okay, but that's one of the parameters that you can play with for your specific task and your data. Different, maybe if you're doing cats or boats, you may require a different setting. All right, so then you give it that test sample, and the Hopfield network tries to reconstruct it, and then it produces what it calls the recalled sample. After it's done the comparison, it produces, it transforms essentially this sample to this. So then what we're going to do is I'm going to move some of this code down. All right, so essentially now we're going to look at the original pattern and the reconstructed pattern. Okay, so I'm going to do that. And there it is. So you can see essentially we want and reconstructed it almost to the same thing. Do you guys see that? So that's pretty good. That kind of signifies that it looks like what it knows, right? But still, well, obviously, we're not going to do a qualitative analysis of it. Instead, we're going to use the Hamming distance, right? The Hamming distance, what's nice about it is you compare all the values. So it says this one's the same, so that's the one, this one's the same, and so on. And it's going to compare each element wise, and then it allows us to compute a distance metric. Here, I just converted the NumPy array into port. Okay, that's all I'm doing. Um, so this one, the first one's the list. So initially I converted it into a NumPy array, and then I converted it into a torch array. I'm not even sure why I did that because this is also in Numpy. So it's probably not necessary, but it can handle it. All right, so I create the test sample and the recalled sample, and then I give those two to the Hamming distance function that I created here. And now it should give me a metric. So let's go ahead and take a look. And there it is, 0. What does that mean? It means that there's no difference. Do you guys understand? That's how it works. Any questions? So that's what an anomaly, what most anomaly detection systems do in machine learning. They will try to reconstruct the input through the network and try to make it, intuitively you can think of it, it'll try to make it into what it knows as much as possible. All right. So if something already looks like what you know, then it's more successful. Yeah, sir. Yeah. Pardon? Yeah, each memory is of that specific pattern. So you can't have one of these that has all the memories in the world. You know what I mean? That wouldn't work. Instead, each associative Hopfield network is about a very specific type of a pattern. So what you would need to do is you would need to have hundreds of thousands of memories, right? Individual ones, which the brain may actually, one could argue, works like that. Because how many neurons do we have? A few, more than a few, right? And people say that whenever you think about something, this part of your brain lights up. And if you think about another thing, this other part of your brain lights up. So obviously there is some kind of localized memory in the human brain. Maybe, right? I don't know. But so this is consistent with that. If you built a robot with a lot of networks, you could, use some of it for some memories and other parts for other memories. And it's just you need to have some kind of an index that knows where to go, or there's something more clever that does that. But this is just super simple, obviously, but it is specific for one pattern. Okay. Any questions, guys? Making sense? All right. So now let's complete the exercise. So now we're going to look at the same thing, but with a pattern that looks a little bit different, right? And see what happens. So what I'm going to do now is I'm going to go back to the code and I'm going to go to this section and I'm going to call this one an abnormal pattern. So let me copy this part. So this is going to be an abnormal sample. And in cybersecurity, this is pretty common. So let me do cell type, markdown, run. Okay, so now we're going to add this part. I'm going to move this down. All right. All right, so the first thing I want you guys to notice is the new sample. If you look at this sample, it's essentially -1, 1, -1, -1, -1. If you look, it is very different from the you guys are humans, you're smart, right? So you can look at this pattern already. You look at the data, and you can see already, yeah, the first column for these samples, they're always positive. Second column, they're always positive. Third column, they're always positive. The fourth column are always positive. So I can tell that's a common theme going on in that data. If I look at the normal sample, it followed that specific pattern. Positive ones in the beginning, positive ones at the end. But now I look at the abnormal sample, and you can see these are negative. So already you know that this pattern is more abnormal, right? So the question is we as humans can do that because we have a brain, right, that is doing this processing for us. But here, for a machine to do this, it's got to have some kind of an algorithm. So this is obviously the algorithm. We've already ran the first pattern through the Hopfield network, and it gave us a Hamming distance of 0 after processing through the memory. So now I'm going to repeat the exercise, but now with the abnormal pattern. So I have a test sample over here. I'm going to reconstruct this. So the Hopfield network is going to try to make that sample look like what it knows. But given that it's different already, it's gonna be harder for it to do it. That's essentially like the intuition of this. So I reconstruct the sample and I'm gonna look at it. So go ahead. And as you can see, it it was not able to convert it. It flipped these two. See how it flipped the ones that it kind of knew about, the ones that sometimes are minus one and sometimes are plus one, but it had no basis to convert to. You see the first two and the last two. So now we're going to try the approach. So now I just take the two vectors, I'm going to run them through the Hamming distance, and you get two. Whereas before, you got a zero. This is, that's essentially the whole algorithm for anomaly detection. So what would happen? Okay, so how is this? Let's say now you build all of this and you want to implement this in your network environment, right? So what does it mean? You have a Hopfield network, lots of associated memories in there. You get a pattern, and this pattern is like good traffic, people just sending email or whatever it is. And so, but it already knows that type of network traffic email. So it just says that's a zero. So that pattern gets, a zero value. Then it sees this one, and this one is not email because it's very different. In fact, now is it an attack? Anomaly does not mean attack. It just means more different, right? So this one could be somebody using a game that has never been in the network. You see that? It's some weird game that's new, or it could be an attack. But the network runs it through its memory and it says, you know what? That's a two. So what happens now is, since the network administrator can't really look at everything, because this is gonna happen thousands and thousands of times during the day, right? So it's gonna create all these, for all these patterns is going to assign a value. So what it does now is it ranks them. So it's gonna rank this one to pop up over this one. So the administrator, the human, never looks at this one even. Because why? I mean, it looks similar to the data, but it will look at this one and then maybe it has to do some manual thing or it has to go to a more advanced network scanner. So that's essentially how anomaly detections in these contexts work. All they do is they provide a value for the pattern. If it thinks it's very different, this value is going to be higher, and the values that are the highest will be the ones that get flagged and ranked to the top. And that's it. Any questions, guys? That's the Hopfield network. And that completes the exercise for this one. So we get the abnormal test. Now, a few things that we can do is we can break down some of the operations, just to kind of visualize them a little bit better. All right, so let's call it breaking down the operation. Go over here and add a few more cells. Breaks out. Breaking down the operations, cell, markdown. There you go. All right, so let's copy that part of the code. So we can visualize a little bit better. This is the part of the code where we are updating the weights, right? So if you remember this in the train loop, this part in the train loop, just essentially this. We iterate through all the patterns. We're performing that NP outer operation. Then we're adding it to the original weights, and they're being updated. Essentially, this does not use stochastic gradient descent or like the things that we discussed about calculus with the perceptron. This is a super simple approach. No doubt, Boltzmann machines and other algorithms try to extend these ideas to incorporate those concepts, but this is the most basic example of that. So now let's take a look at this code. So we know that the size is 6. So then it's NP0 6 by 6. We've got the weight. We iterate through all the data. We can print out the NP hour right, for that particular sample, and then see how it modifies the weights. Okay, so um, so we can also print. Not sure why I didn't have that. Weights. Yes, print it. Both of these should have the same dimension. All right, let's go ahead and do that. I think it does. Yeah, so you can see there, it takes the vector, right? It computes the NP outer operation of it, and then that is added to the weights and modifies it over time. And this, then we take the second pattern, we perform the NP outer on this, and then modify the weights. If you look, the weights are starting to change. Do you guys see that? So, here they're ones, now it's twos, threes, and so on. You can see how this is starting to change. Fours and so on, not all of them, right? But see, that's where the pattern recognition is starting to happen. The algorithm is starting to create this set of weights that is going to allow it to essentially have memory. Okay. Now, you might argue, you know, how did you, where did that come from? Well, I mean, it came from the mind of a person that won a Nobel Prize, right? So this is a fact, right? So anyway, so that's the idea there, right? Then we have, I believe I have the other operations. Um, yeah, the diagonal, so you can see that. So the minus I, the identity matrix, and that sounds very complicated until you really think about it. And all you're doing is, whereas before you had here, see, these are for these diagonal values. That's called a diagonal in a square matrix. And whereas they were four before, now they are zero. So you don't want weights, self-connection weights. Okay, you don't want that same neuron having a value. Okay, so that's essentially part of the algorithm. Okay, and then these values are normalized in the algorithm. They're divided by the length. So the length is 4. So notice over here, that's also in the training function. So weights divided by however many samples we have available. So I can just print that here. Run it. See, the values have been like normalized essentially. So divided by the number of samples. That's it. That's the whole, all the code that is here. See, these steps, the for loop, putting the zeros in the diagonal and then divided by the number of patterns. Okay. And that essentially, if you look, what's really nice about this is obviously it learned something. Right? It got about that, right? So it learned something about the images, and so that could be what memory looks like in our brain. I don't know, right? But it gives you a little bit of an insight. At least this is a synthetic representation of what memory can be. Yeah, please. Don't even try to. I won't even pretend. I can see what you're saying. Like you're trying to say the positive or probably a positive correlation and negative and negative correlation, maybe likely. But with neural networks, you actually never know exactly because they can think. I mean, this is actually a very interesting thing, right? So move 37. So move 37 means that when AlphaGo is a neural network that was built by one of the big research AI labs, right? And they built AlphaGo, which is an AI that played a game called Go with Lee Sedol. I think it's the champion, the human world champion of that game. So they were playing, he's playing with AlphaGo. And everything is going, it's interesting, but then comes move 37. This is very famous. Move 37, the player, at least say, was just like, what is this? Because it made no sense. It was a move that, like, the game was almost like, it seemed like the AI was throwing the game, in a sense. Almost. It's like, it was losing a very, I don't know about, but it was, chess is losing a very important position or piece. But that move 37 was significant. And after that, the AI just took over and won the game. And so but the point with move 37 is the neural network thought of something that humans in thousands of years have never thought about. And how is that captured? It's captured by the weights. So even though us as humans would say positive means this and negative means this, remember there's like multiple of these. So it may actually be thinking, this is where now it gets a little bit scary of how AI thinks are thinking about new ideas and may even have new ways of thinking. So I would agree with you where you were going, but with a little note that we don't quite know as these things get really big, exactly what's going on in there. Yeah, are you talking about the game of Go?
Yeah.
It's just, it's like in chess, right? I don't know if you ever play chess, but there's certain moves that you take and certain strategies, like the Queen's Gambit or something, do a specific. But so for Go has existed for thousands of years, or at least hundreds of years, and everyone knows, well documented, all the moves. But that move that happened, famous move 37, was like no human had ever seen that.
AI.
It was a pure AI image. Exactly. It's pure AI engineering. And so the thing is, it was a crazy move also from the perspective of a human. Because it's like somebody playing chess and you all of a sudden on the third move kill your queen. Intentional. But yet you still win the game. Because that's central to the strategy that you're building. You see what I'm saying? So you can look it up. It's very famous. For instance, in ChatGPT, everyone's currently still waiting for that move 37. That moment where it's gonna do something. It's like, wait a minute. So these neural networks, my point is, they're not, although they seem like um, they are mimicking our brain, they may not actually be mimicking our brain. This is a creation of humans, right? We're trying to mimic the human brain. But humans are smart, right? And so they have other tools that biological entities didn't have. Think about that, right? Like the brain, for instance, think about how the brain evolved very slowly by doing these random mutations, right? That's how the brain evolved. But humans are so smart that they have created other ways of doing things. So it's not quite clear. But you were right in your thinking. Do you have another follow-up question? Or? Yeah, no, it is very interesting because that's why when it comes to the weights, I'm a little bit, especially because we are looking at the weights right here, right? So we are actually looking at how it thinks about them, and this is dependent on the algorithm, also very dependent on the objective function. Whatever the goal is for the task, also you have to keep that in mind. It's gonna optimize it for that. Right? So that's why I was saying, like, another example of this is if you're building a system and you ask it to reduce traffic in Chicago, well, that's the only objective you gave. We as humans have certain things that we know, like we don't harm other humans, right? But if an AI does not have that in its programming, it might just think, well, the simplest thing is I'm just going to nuke Chicago and no more traffic. You see what I'm saying? I mean, we don't know how it's going to think about something and what the ways are going to represent. But yeah. All right. Yeah. So let's keep going. So we have a few minutes, but that was a very good question. And it's very interesting. Check out AlphaGo. I think there's a Netflix special on it even. So you guys can check it out. It should be pretty interesting. All right. Also, that's like 2015 technology, and it's now 2025. So it's been 10 years since then. So let's keep going. All right. So we looked at the ways of very nice. Now I want to show you just very quickly. I don't really have data, but I want to show you that we can also encode other patterns. For instance, when we had images, cats aside, you wanted to create an associative memory of cats, right? So how would that work? So I'm just going to use some random data here. The control copy. I'm going to do cell, okay, markdown. So example, assuming samples, so images of size 10 by 10. So this assumes obviously, say you got thousands of images, they all have to be 10 by 10. And you just want to memorize what that looks like, or a dog or something. So here you're not trying to differentiate between cats and dogs, right? Remember that. Here we are actually trying to just learn what a cat looks like, essentially, or something. So how would that work? So we can think about that idea here. So I'm just going to use random data. So essentially what I'm doing here is I'm creating, so because the image is 10 by 10, when we spaghettify it and make it from a matrix into a vector, what's the size of it? 10 times 10 is 100, correct? So I'm going to create an array that has 100 zeros and 100 ones, kind of in that order, and I'm just going to convert that into a Numpy array. So you can see that there. So I have that. Then I'm going to randomize it. I just do this here. So, random shuffle just will shuffle the zeros and ones. And then I'm going to make this, I'm going to reshape this from a vector into a grid. So now it's essentially an image. Do you guys see that? So this is an image. This is actually how many of you probably have your L in your homework assignment of PyScript, right? This is kind of what you have. And currently you're not displaying. So that's one of the things that I wanted to show you is that we can take data like this and kind of make it into an actual image from a NumPy array. Got it? So that's kind of the idea. So we need to import from help import image. Let me see if that works. Okay, so that will work just fine. Pale is a Python image library, standard library for a basic one, but powerful. Yeah. So now what we want to do is we want to convert this NumPy array into an image so that we can actually view it. And we're going to use this library. So, all right, so we have this the image. So my IMG would be image dot from array, and this one is image. Okay, I'm gonna run that. Okay, no errors, right? So now we can save it, which is actually something you guys might need to do. So that would be my IMG dot save. Whoops. And this should be PNG, I think is the default. Oh yeah, sorry. And this should be some name, the image dot PNG. Okay. Okay, no errors. So we can take a look over here. Here's an image. You guys see that? The image PNG. And it's very tiny. But there's an image there. So my PNG. And it's very small. Well, we can fix that. 500. What is half of 784? What is half of 784? Now, an even number. What's half of 784? Huh? 342? 342? Huh? 92? Just a 784 is a nice reference to use. All right, so that should create a pretty big image that we can see and shuffle it, zeros and ones. Oh, yeah, this is now 392. Or sorry, this is 24. 28. 28 times 28 is 74, right? Okay. 28, 28. All right, so we shuffle it, and then now, and so black. Um, sure what's coming out. Change. But you guys get the idea, so I'm going to change this to 5. Okay. But I'm not doing something at all black. And I would have expected to see some values. I feel like I need to tell if it's binary. Hmm. This is what I was trying to show is, let me do this. So rand array np dot random and int low equals 0, I to size equal 100 by 100, data type equal np dot int 8 and equal image dot from array rand array times 255. Yeah, see, I was trying to create something like that, kind of a random image. I don't know why. I'll have to look it over. Pardon? Huh? Oh, what? A QR code? Yeah, it's just noise. That's what noise looks like. I would argue. Because I just created a vector of random data in it, and then I squared it, and then I made it into an image. Essentially, it's just noise. I was trying to do the same with the approach with this approach, because then this is kind of how you have your T's and your L's, so you create the image. I'm missing something here, obviously, but you guys can see the image from array and this random that's the same. I had it here. And this is the array, which is an numpy array at the end, but the size doesn't really matter. I think I even did it as 100 by 100 or 784, actually. So I just created some zeros and ones, shuffled them randomly. And I feel like it's the data type that I use. So typecasting it to integer, maybe. Let's see. I'll try one more and then we'll move on. NP dot array image D type equal NP dot U 8. See if it takes that. I think it took it. Oh, it worked. Yeah. So it did work. So I guess it was the data type. It wasn't liking whatever it was. So I just all I did is I changed the data type to U and take like an integer. So if you guys have, I'll load this up in the 2025 thing, but if you guys want to do this for your PyScript homework, that's fine. You can take your NumPy arrays as TNLs, run this code, generate the image, and then display on the website. It's entirely, yeah. Not yet. You're right. I got really stuck on trying to do this for the homework. I have not used it. You're right for the Hopfield network. So that's a good valid point. So what I was showing is essentially the pattern before was a vector of size 6. But I'm trying to show you that you can also use the Hopfield network to remember images. So the way that you do this, I kind of did it in reverse, right? So I created a vector and I made it into a grid. You would do the opposite. You would take the image, flatten it, and now whatever that size is, that's how you train the Hopfield network. Do you guys see that? So that's essentially what I was showing. So yeah, I got kind of sidetracked there. Um, so then what would you do? So remember your values are kind of these zeros and ones over here. So you want to encode them as we did in the Hopfield networks with -1 and +1. We use this little formula to convert it to polar values. So we just do this over here. So now I have to find, so I've made changes. So maybe here. It was called image, I think. Yeah. So would you just do that? Print it out. Now now I have to remove. So if you're doing the image, you'll have to do this, okay? But if you're just doing it for the Hopfield network, don't do that. So instead, run it from here. And as you can see, I've encoded it now in the way that we have the Hopfield network. Does this make sense, guys? So one approach was to convert it into the image. I used a uint8. This one here for pill images. Otherwise, we just convert it into the format of 1 and -1 that we have been using for the Hopfield network. And from there, we would repeat it. So you can see it looks like this. And then you flatten it, right? So you have this idea of flattening, which is what I call sometimes spaghettify. So to flatten, now that you run it, now it's just a vector, essentially. And yeah, so we would do all these steps. But we're out of time, I guess, for today. It's 3:40. Okay. Hopefully that made sense. All right. I'm not gonna assign a homework for Hopfield networks. You have your home, your actual homework assignments, but this concludes your third machine learning algorithm. We have made it in 1981.
Have you been in like
We were in the 40s, then 57. And now we just made it to 1981. The 40s, 57, 1957 was the perceptron as we learned it. And then, don't worry, 85 is the very old. So Canaan is very old. Euclidean, the essence of Canaan is the Euclidean distance, so Euclid. Don't worry, the nice thing about